Good evening, good evening, good evening. That's better, I hope. We've got a mic actually functional on that. First technical hitch of the evening. We're going to look at work, energy, power, kinetic energy, and potential energy. So we're going to start with work done this evening. So we've got this idea of work in physics, and it's annoying because we use the word work in all sorts of other areas of our life, but it's a very technical physics term. Okay, work done is a measurement of energy, and as such is measured in joules. Okay, capital J for that, and has a very specific description that the work done is defined as that work done is equal to the size of the force multiplied by the distance an object moves. And that is a mathematical description of it. That is an equation we absolutely need. And again, if you're not the biggest fan of maths, because it's a three-part equation, it does form quite a nice equation triangle where you have work done at the top, you have force at the bottom, and you have distance moved at the bottom corner as well. So if you cover up one, what remains is how you calculate that. So let's grab ourselves a little circle just to remind ourselves how to do that, that if we're not the world's most mathematically savvy, which you should be getting to at this stage of the year, but let's ignore that. So if I want work done, I cover up work done and I'm left with force times distance because they're beside each other. If I want distance traveled, I do work done over force as a fraction. And if I want the force, it's the work done divided by the distance. Right, and that's pretty much all there is to it. Force by definition has to be measured in newtons. Watch out for kilonewtons and things like that. Distance must be measured in meters, and that's an examiner's dream, that one, because you can put kilometers in there, you can put millimeters, you can play around with all sorts of stuff. But fundamentally, it's a three-part equation. Know the equation and work through it. The more interesting concept is in fact the second definition of work, which is a word-based one, which is that work done is equal to energy transferred. Energy transferred. My keyboard skills still not getting better despite what 9-10 weeks of doing this. So transferred, talking and typing is not easy. Right, there we go. Use the autocorrect. Right, so work done is energy transferred. So if I move energy from one form into another form, I by definition have done work. So if I turn kinetic energy, the movement of an object, into potential energy because I've put it up in the air, I've done work. If I convert chemical energy into heat energy, I've done work. The movement of energy is work. This is a warning. Okay, this one here is a warning. This is because it doesn't come up as an equation. It tends to get overlooked in revision, and that can be exploited. That's a really good differentiator between who's gone, made a list of equations, just learned that and walked into an exam, and who has really studied their notes, worked out what it is, and understood the concepts that are going on. So here we can expect some form of differentiation question, and we'll come to one later on when we have a look at that. So this is work done. Simple example. Let's see. Let's take a nice little block. Set it on some form of plane like this. I say plane. That's not airplane, of course. That is a flat surface. Give that a little bit of an autofill. Give that fill in there. That. Give this thing. Yeah, we don't want that color. We outline. There we go. Okay, so we're going to take this object, bring it to the front, and then we'll have a look at this. Right, so I'm going to drag this object and I'm going to drag it across the floor with some size of force. So arrow that way and a force of, let's say, 40 newtons pulling it. And let's say that we managed to move this thing a distance. We're going to put a distance in like that. We're going to drag it all the way across there, and that distance is 25 meters. Okay. So all we do here is we apply the equation. I want to know what the work done is, so I go work done is equal to force multiplied by distance. Therefore, the work done is equal to my force. Is it in newtons? Yes, it is. Multiplied by my distance traveled. Is it in meters? Yes, it is. And these are the questions that are going through your brain as you're answering these questions. And then we get the work done is equal to 1,000. And then we check our units. We've got our basic units, so we know that work done is going to be measured in joules. Simple. Now, we immediately run into the problem of if this is all that's going on, then we could maybe make the argument that a snail is as powerful as a sports car, because if a sports car can travel 1,000 meters and it pulls a load, of let's give arbitrary number. Let's say it puts 10,000 newtons forwards, and then we can do the calculation in that. We could argue that something else, anything else like a truck, is pulling a much greater force over that distance, and therefore is by definition a more powerful engine, and is doing more work. But we need to also recognize that the sports car is going to do that faster, and that's got to be a factor. That's got to be something that we put into our equations. It's got to be something that we have a little consideration with. That if you've got an Olympic athlete running up a set of stairs, they're going to run up that set of stairs. They're going to be reasonably light and in shape. They're going to bound up the set of stairs. They're a small force because they're working against a small amount of gravity because they're light, up a set distance of stairs. Okay, if I get somebody who is gravitationally challenged to do the exact same process as they meander their way up the stairs, then technically they've done more work, and they absolutely have. They have taken a much larger mass, travelled up a set of stairs that is the exact same as the Olympic athlete, and therefore they will have expended more energy. But that doesn't mean to say that your Olympic wall climbing team, if such a thing exists, should be consisting of people who are as massive as you can possibly make them. That would be foolish. And the reason for that is that we care about how long it takes. And this runs to our next concept. Our next concept is the concept of power. Okay, now power is how fast you do work. The faster you can do work, then the more powerful you are. Now run that thought in your head. The bigger, the less time it takes you, then the more powerful you can be. And as a result, we're then going to need some form of fractional relationship with time on the bottom. Okay, because as the time gets bigger, the power must necessarily get smaller, and as the time gets smaller, the power must necessarily get bigger. This is an inverse relationship. They're the flips of each other, mathematically speaking. And then what is it that we're doing in this time? Well, we are doing work. So power is equal to work done divided by time, and the time taken to do that work. And again, we've got 3 parts to an equation, so we can form a triangle in this one, but we need to be careful. Because we express it like this, power is equal to work done over time, then power actually ends up in this bottom corner here, P. Work done up in the top corner, WD, or E for energy if you fancy, and then T in the corner for time. So we can immediately see, as we're developing this triangle, that work done equals power multiplied by time. And that's another equation to add to your bow. And that the time taken to do anything is going to be the amount of work that you do divided by the power of your machine or you or whatever it is that you're having a look at. All right. So again, let's run ourselves back to our little problem here, where we have our 40 Newton force moving 25 meters, and let's add yourself a little bit of extra detail. Let's say it does that in somewhere around about, we'll keep the numbers nice and simple, we'll do that in 100 seconds. Right. And once again, we need the standard units here, so we're using seconds, and we should be looking out in exams for minutes, hours, days even, if we're talking about maybe planetary bodies or something along those lines, or snails or anything like that. Can we convert back to seconds, because we need standard units. And we want to find the power. Okay, so let's grab our equation that power is equal to work done divided by time. Okay, so the power is equal to my work done. Now, in this case, I've already got my work done, but I might want to take a little bit of a step off to the side and calculate that, or I'll show you in a little second, if you're pretty good at one-step calculations, how to do that all in one go. But in this case, we have 1,000 joules of work being done in 100 seconds. That was handy, wasn't it? Okay, so we've got 1,000 divided by 100, so we've got a power of 10. 10 watt, I hear you say, because we haven't discussed a unit, and you're exactly right, 10 watts. The unit of power is the watt, W-A-T-T. My mother's maiden name, my singular claim to fame when it comes to science is that I must have some form of relationship to this equation somewhere. Okay, so this is us, this is power. and it is fundamentally the rate at which you do work, and is a cornerstone to the 6-mark question on how to measure your personal power, how you would measure the power of either a motor or a person or anything along those lines, and you have to set it up in that way. So we'll take a look at the expanded form of that equation, which is that power is equal to, instead of on the top line work done, if we haven't already calculated that, we can do it as force multiplied by distance, and then we want to divide that by time. Okay, that doesn't seem particularly useful because you can do force times distance over at the side, but what does become more useful is if you multiply both sides by t, you end up with power multiplied by time is equal to force multiplied by distance, and this then can be a useful thing for isolating the force or isolating the distance or anything along those lines. So that may have a fringe use here and there in your exam. Alright, so let's consider slightly different situation. Let's have once again some form of surface down at this, and we'll fill that in, and we're going to actually lift an object. Let's get a little round object for a change. We're all about switching it up, and we'll make it a nice little green color. And what I'm going to do is I'm going to move this up by a distance of, let's say, 4 meters. Okay, and I'm going to tell you this thing has a mass of 2 kilograms. So we're going to have to pull in a little bit of extra information here. So my question here is, what work is done here? Alright, so we want to go work done equals force multiplied by distance. And then over at the side of the page, I'll have a little bit of a doodle out. I know that's my equation. I know this is a calculation based equation. So I know the distance is equal to 4 meters. The force that I'm going to need to pull it up with is a little bit elusive at the moment. I don't have a force on this diagram. I have a mass certainly of 2 kilograms, but I don't have a force. So I need to have a little think about what's going on over here. Well, in order to lift an object, you must overcome the gravitational pull that is trying to pull it back downwards. So in order to lift this object at all, I'm going to need to provide a minimum force that is equal to the weight. And hopefully we remember from our work on forces that weight is equal to the mass of the object in kilograms multiplied by the force of gravity acting on it. And weight is a force, it is measured in newtons, and therefore we need mass in kilograms, and we need the force of gravity in newtons per kilogram. Now it's handy because on planet Earth the gravitational field strength, the acceleration due to gravity, or the force of gravity, whichever way you want to put it, is equal to 10. So that gives us 2 multiplied by 10, which gives us a weight equal to 20 newtons. So on my diagram then, I can add that force in. I know that I've got a downward force acting in this of 20 newtons. And here's the tough bit to get your head around. In order to lift this object, I will need to produce an upward force that is also equal to 20 newtons. Now, naysayers amongst you might say I need more than 20 newtons, and that's a fair point, but I actually don't. I only need more than 20 newtons to get it moving in the first place. After that, 20 newtons will do nicely. If we remember from our discussion on Newton's first law, an object will continue to travel at a constant speed provided the forces on it are balanced. These forces are balanced, so if I give it any speed whatsoever in the upward direction, it will continue to do that. So 20 newtons is the force required here, because the extra upward force to get it moving could be 20.0000000000000000000 and so forth 1, which is 20 for all intents and purposes. So the force I require to lift this thing upwards is 20 newtons. The force required to lift an object in the vertical direction is exactly the same as its weight. So now I've got the requisite bits for my equation. I can pop over here and go work done is equal to 20 multiplied by 4. The work done is equal to 80 joules. Brilliant. Now, all the way back to the start here, though, we did say that work done is equal to energy transferred. So if I've done work, I've transferred energy. So I've transferred 80 joules into something. But when it gets to the top here, it stops. So it's certainly not movement energy. It hasn't heated up. because we're not running it through any form of material where friction can be occurring, because we've assumed we're doing this in a vacuum. It can't do anything else, so we say that it is stored as gravitational potential energy, GPE, gravitational potential energy. And the gravitational potential energy, which is written as E subscript P, that's energy in the potential form, is equal to the mass multiplied by the force of gravity multiplied by the vertical height you raise this thing. Okay, which again seems like a brand new equation, but actually isn't. It is an amalgamation on a rewriting of this one, because if we look here, we have work done equals force times distance. I'll just highlight that out for you. Work done is force times distance, but the force I'm using is mg, just here. And then I'm going to multiply that by the distance, and I'm going to try and get myself a different colored box. So let's get a red one. We have this letter H over here. I really shouldn't have used the fill. I wanted to use the outline tool there, but loving it so far. So we want a fill color. We actually don't want a fill, but that'll do. We'll do the way we are. Line color, the red. I'll put that in behind. That'll work. Okay, and we want to send that to back. Okay, I've got H there, but H is in fact just the distance. Okay, so gravitational potential energy, EP, is in fact a measurement of work done. Or the other way around, the fact that you've gained gravitational potential energy means you must have done work, and the amount of work is equal to your gain in gravitational potential energy. These are the same thing, though absolutely you should learn the potential energy equation as a standalone one itself. Okay, which brings us to potential energy. And that potential energy arises from the idea that if I put something above the ground and leave it sitting still, that if I displace it or let it go, it will fall, which is a problem because at the moment it is not moving and not exhibiting any form of energy things, and then suddenly it starts developing kinetic energy. So therefore it must have the potential to start moving. It must have the ability at some point in the future to start moving, so this then becomes a system where we have gravitational potential energy. EP again is equal to mgh. Subscripts are fun. It's better. Now this is a four-part equation, so it's a little bit more tricky in terms of managing it with a triangle, but it can be done. That we have EP up at the top, capital E ideally, capital E ideally. That's better. Let's try that again, shall we? Capital E subscript P is equal to M multiplied by G multiplied by H. So we've got three things on the bottom line of our equation. So what we need to do is we need to divide that up into three sections. So divide that up like this. And this then leads to other equations that run from that. So we'll go back to having our little filled in circle so that we can discuss how we then get that. So grab a little yellow circle. So if I want EP, it's mgh, because we've got them m times g times h. More interestingly though, if I have h, I then end up with E subscript P is equal to, H, apologies. H is equal to E subscript P divided by mg, because we've got E at the top here and we've got mg on the bottom, so it's EP over mg. Similarly, that if I want to have a look at what is the mass, then I'm going to have a look at m is equal to, top line says EP and the bottom line says GH. Okay, so this is the concept of potential energy. Right, so now we're going to let it go. Not in the frozen sense, but in the physics sense, and it's going to roll down here and hit this table. And because it's going to do that, it's going to gain speed. And it's going to gain speed proportionate to the amount of energy that it actually has. That if you drop it from a high up place, it's going to gain more speed than it is if you drop it from a low down place. So let's have a look at the equation for that. This then becomes the equation for kinetic energy, E subscript K. And that is equal to a half multiplied by m multiplied by v squared. Okay. Standard physics equation here. Go and learn this one. It's a little bit tricky in that place, but it can be done. It can be done. This then tells you that the energy that I have in the kinetic form is equal to 0.5 multiplied by the mass multiplied by the velocity squared. And it's just the velocity that's squared. That's critical. Okay, it's not the whole thing, just v squared. So quick example on that one. Let's have a block of mass, let's say 500 grams. Give you something slightly more difficult to do, is moving at 16 meters per second. How much kinetic energy does it have? So that's a straightforwardish one. Then we pop that into our equation, and that gives me that EK is equal to a half multiplied by, now 500 grams needs to be converted to kilograms because masses are in kilograms here, so that is 0.5 kilograms multiplied by 16 squared. Right, now you can have a crack at doing that in your head, but I would strongly recommend against that in an exam situation because your head is not exactly reliable. I'm trying to type and talk at the same time, and I'm not managing it. If you're trying to manage your emotions, your stress, and all sorts of things in an exam situation, then you probably don't want to do that either. Grab the calculator and just get it done. So pop that into your calculator and you end up with 64. And again, because this is an energy, and all energies have in common their measurement system. Okay, they're measured in joules. So 64 joules of kinetic energy is available in this system. Now, the kinetic energy equation doesn't lend itself massively well to a triangle, but again, it can be done in much the same way as the potential energy one is done, that E subscript K is equal to a half at the bottom, 1/2, times the mass times V squared. Now, if you are using this as a technique, and there's nothing wrong with that, there's no judgment here on the channel, what you really must have a little bit of a think. What you really must do at the end is you must square root V squared. Okay, you are not going to find V with this process. You are going to find V squared with this process. All right, so let's cover up V squared and see what happens, because everything else is relatively straightforward. It's what you would expect to happen in any equation. So cover that up, and we have that V squared is equal to EK divided by a half, which I'll write as 0.5 here, times m. And you just pop that into your equation, get the number out of that, you'll get a single number here. But your very, very last point is that you must recognize that you have found V squared. So you must square root both sides of your equation. You square root V squared to get V, which means that you have to square root the other answer that you get on this side, and that will give you V. And for the really high level mathematicians in you, that means you get two answers because you get the negative one and the positive one, though we'll usually be interested in just the positive value. So comment and chat if you were finding the velocity, do you square root last? Absolutely. You square root at the very end, having found V squared. Okay, isolate V squared by itself, calculate the value on the other side of the equation, square root both sides, and you're done. All right, so now we move on to the roller coaster question, as it's usually described by teachers. Okay, so let's get ourselves some form of track here. I really need to get myself a drawing tablet. Actually, I don't, because it gives me an excuse to have really crap diagrams. Right, so let's pop ourselves a little object at the top of this hill. Let's tell you how high the hill is. Let's tell you how heavy the object is. Let's give it a mass of, let's make it not small, 200 kilograms. And it's going to be a height of 8 meters above the ground, and it's going to come flying off the end here with some form of speed equal to V. Okay. And we want to find out what's V. Assuming that there's no energy lost in the process, though we may have a little chat if time allows what happens there. So in order to do this, we need to have the principle of conservation of energy in our head, and that is that energy cannot be created or destroyed, but can change from one form to another. Now, that's nice, but for the purposes of actually talking about this, for this example, all we need to say is that the total energy remains, there's an R in energy, remains constant. Burn that into your brain, and you can do this question with relative ease. So we're going to assume that this object is stationary to start with, though we can make it more difficult by having it moving. Up here then, we have two forms of actual energy that this thing can exhibit. It can exhibit potential energy, EP, equal to mgh, and it can have kinetic energy, EK, equal to a half mv squared. And adding those together will give you total energy, we're going to just call it total, equals. And we're going to go and do that calculation. So we're going to move it down here and have a little crack at it. Okay, so EP equals mgh. So EP equals the mass of this object, let's take a roll up, 200 kilograms, multiplied by the force of gravity on planet Earth, which is 10, multiplied by the height that this thing is at above the ground, which is 8 meters. So EP is equal to 200 times 10 is 2,000, times 8 is going to be 16,000. Okay, so it's got 16,000 joules of energy in the potential form. Its kinetic energy, for the sake of doing the equation, EK is equal to a half mv squared, which is a half times 200, and we said it was stationary to start with, times 0, so its kinetic energy, EK, is equal to 0. We could have said that just because it's not moving, but it's always useful to show that by maths because you should be in the good habit of doing both of these steps. Alright, so what does that mean? It means up at the top we have EP equals mgh equals 16,000, that EK is equal to 0, and therefore the total is equal to 16,000 joules. Now this is critical. If we don't have energy losses anywhere else in this system, we're not losing heat or anything like that to friction, then no matter where I do this calculation, okay, be it here or here or here, or actually where we want the answer here, the total amount of energy of that system is going to be 16,000 joules. So the way to approach this sensibly is to then come across to here and do EP equals mgh, the exact same thing that we did at the top. EK is equal to a half mv squared. Once again, the exact same thing we did at the top, and then total, made an equal sign in there, the total is going to equal, but this time we're not leaving it blank because we know that it's 16,000 joules. Is that alright, everybody? Just shout if you're not happy with that, but it looks like we're okay. Okay, so we've got 16,000 joules total energy lying here. Okay, so to the calculations. We want to find EK out of this because we want the velocity. So the likelihood is that that's going to be the last step we do. So let's take a look at EP. The potential energy, EP equals mgh. So EP is equal to the mass of the object, 200, times the gravitational field strength on Earth, which is 10, times the height it is off the ground. Well, it's actually now down at ground level, so that's 0. So the potential energy, EP, is equal to 0 joules. Straightforward enough. And again, we could have just skipped that step without proving it, but I like completionism. So if the total energy is 16,000 joules and none of that is potential, then the only logical outcome then is that the kinetic energy has to be 16,000 joules. It's like saying Johnny has a pocket full of sweets. They're either red or blue. None of them are blue. It doesn't matter what number you give me for the number of sweets, I know that's the number of red sweets he has in his pocket. So EK is equal to 16,000 joules. And we can now use that. We put our kinetic energy equation with numbers in it this time. That 16,000 is going to equal a half multiplied by the mass, which is 200 multiplied by v squared. Okay, so 16,000 is going to equal 100 v squared. Okay, dividing both sides by 100. I'm doing this by the long maths method, by the way. You could have absolutely gone v squared is equal to ek over a half m and just gone for it that way. I prefer doing it this way. We're going to divide both sides by 100 now to give you 160 is equal to v squared. And be careful here, because this is where a lot of people drop out. They put 160 down, but you haven't found v yet. You found v squared. So you need to take the square root of 160, and that gives you 12.65 is equal to v. So my final answer is equal to v equals 12.65, and since we've used standard units all the way through, our unit for velocity is going to be the same. It's meters per second. Now it's 9 o'clock right now. I would normally stop at this stage, but because we are revising for triple award physics, we're going to take a look at this point here before leaving. What if I want to know what's going on here? Okay, and here is the point. Let's make life properly difficult for ourselves. This is 3.5 meters up off the ground. Okay, so I'm going to clear out some of the unnecessary stuff here for this equation. I will leave that one in there. That might be useful. So what do we know? We know that it's going to have two forms of energy here. It can only have two forms of energy. That is EP equals mgh and EK equal to a half mv squared. And in very large red writing right above this, it says the total energy remains constant. So it doesn't matter where I am on this slope, that we have the total energy is equal to 16,000 joules. And I'm interested in finding it out. Stardust Dragon, I appreciate this. Actually turned up on the double award paper last week. Yeah, so we want to find out what's going on at this point. Okay, so we add these two together, and we're going to get 16,000. But this time, there's no zero involved. This thing has potential energy. It's off the ground. This thing is moving. It has kinetic energy. So we need to have a little bit of a chat and a little bit of think about that one. Okay, so EP equals mgh. I'm going for that one first because A, it's simpler to calculate, and B, it seems logical that this is what I'm going to want to do, because I'm being asked to find the velocity. So I'm going to end with the kinetic energy equation. So EP equals 200, which was my mass, multiplied by the force of gravity, which was 10, multiplied by 3.5. Okay, so my potential energy is going to be the product of all three of those. And that number, as we can see from the maths, probably straight away is going to be less than 16,000. If it isn't, we've got a problem. And it's equal to 7,000 joules. Okay, so let's pop that information in here. That we have our potential energy is equal to 7,000 joules. All right. Well, now we can see by a little bit of subtraction that if the total is 16,000 and 7,000 of it is potential energy, then by logic we are going to have a kinetic energy that is the difference between those two things. That this is going to be 9,000 joules of kinetic energy straight up. Okay, because 7,000 plus 9,000 is going to give me the 16,000. And then we're back to the exact same process again. We want to use that EK is equal to a half mv squared. But we know that EK is 9,000, so we can pop that in, equals a half, multiplied by the mass, which was 200 times v squared. Sort out the half times 200 times v squared thing, collect those terms together. Any first years watching, this is what algebra is for. Gives me 100 v squared. Divide both sides by 100, and that gives me that 90 is equal to v squared. Okay, and again, we haven't finished. We still need to then square root that 90 to give us 9.49 is equal to v. So my final answer here is that v equals 9.49 meters per second at this point. Okay, now Occasionally you can get asked, as it moves from here down to here, it's 3.5 meters off that, and it loses 2000 joules as heat. Well, that then just becomes, let's just, before we go, let's just take that one last thing. That then challenges our assumption that it's just EP and EK in here. We would actually have to write that heat appears in here as well, and we've got 2000 joules of heat, which when I was doing my calculation at the early point would say I've got 2000 joules of heat generated, 7,000 joules of potential energy generated, so therefore I can only have 7,000 joules of kinetic energy. So we apply that and then we go through the same process. Okay, just realized the thing at the side says betweak. There we go, that's what you get for writing too fast. Okay everybody, that is a whistle-stop tour of work, energy, power, potential energy and kinetic energy. Any questions you have on that, please drop them in the comments. I imagine that this is a topic we might return to because it is going to be a question. The double award paper had it as their last question. It was a beast of a 6-mark question. It was very, very interesting. Good question, but definitely one where you have to think about it. And this is the key. Total energy remains constant. All right, I have had a great time this evening with you. I will see you all at school tomorrow. If you're not at my school, I will probably not. That would be disturbing. Always remember, physics rocks. It's true.